Hi there, my name is Vera Innerlight, and my creator is making Kigurumi masks for more than 16 years. And today we want to talk to you about the durability and structural stability of Kigurumi mask shells. Well, because it is a bit serious topic today. Nowadays we know that a lot of Kigurumi masks that are produced today get damaged during transportation, during use, and there are several causes for this, and it may happen to poor handling, poor packaging, but also there are other sources of these problems is that the masks themselves are poorly designed by the measurements of how structurally stable they are and how the forces propagate inside the mask, and there are a lot of unnecessary force concentrations, load concentrations, and since I am not just an artist, and we also have the knowledge about the deep knowledge about the materials, the deep knowledge about load propagation through the different materials and different structures. Well, actually, we spent some time being an engineer in a department that was responsible for making some kind of construction that would support space rockets, so that not the rocket itself but the structures above the rocket to load it to the table, to unload, etc. Well, so and I was responsible to calculate some of those loads, or some of those forces, stresses inside the material. So, well, I know what I am going to talk about. And so I would focus about in this talk about what can cause the unnecessary stresses in the mask, and to make the masks to crack easily, and why. So when you would design your 3D models for 3D printing, it's mostly important for 3D printing since the fiber reinforced masks, the fiberglass masks are made differently, and they do not have this specific problem, and I will talk why also. So again, about why them. So the first thing I want to talk to you about is the placement of the connection points between the face part of the mask, because there is a lot of masks that currently are made of two parts, the full head masks. So the connection points between the face part and the back part, and how to place them around the mask to reduce stresses inside the material, and to also make mask last longer and make it, well, more structurally stable. So let's get started. For this part 1. Again, so this is the 3D model, the mock-up of the Kigurumi mask I recently designed, and this blue line is the seam of the mask, so the face part and the back part of the mask. Well, I just draw it so we can see what I'm talking about. And let's get to different ways to place the locks on this line. So how we would connect the front part and the back part, where we put the locks, where we put the hinges, and how the position of these parts would affect the stresses in the mask and the durability of the mask as a whole when it is used, when it is at convention, at foot session, etc., 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 whatever use you would have to the mask, with the mask. So the first is where the modern Chinese makers usually put their clasps on the mask. Well, here is this is the video, so the photo of this. So you see above the ears, usually they put their clasps. And here I put the schematic position of this. So one on top is the hinge, obviously, or sometimes it's magnets, and the two clasps, some like here is this position over the ears. And what does it have? So let's draw the load so that the face experience during the wearing when the mask is put on. So we have the weight of the mask. Around here, this is the center of mass of the mask. Also, the head of the wearer pushing against paddings. Paddings usually are at the forehead area and at the cheek area. So here we see the loads for these parts. And the thing is, when you move around, when you dance, when you play, when you do some other stuff in your kick, then when you do all this stuff, then you may be too excited, and the acceleration of your head can be pretty serious. Also, you may want to push your head against a wall, against other Kigurumi, against someone around. When hug itself, you do all that stuff, you move, you push it one way, the other way, etc., etc., etc. And these loads have to be distributed from the front part to the back part. The back part also have the loads, but since we need to know the loads on these specific points, we do not need to draw the loads on the mask. We can treat one half of our mask as some kind of solid object, and the other half as the moving object that we need to find our loads. So in this case, the top of the mask at the hinge area usually pushed towards the back side, and at this clasp area mask is usually pushed away. So you see this is the approximate stress against this part of the stress is when the face pushes against the back part, and this is part of the stress when it's not the stress, basically it's an area where the mask, the face, is pushing off the backside. Also, because you have the paddings, you cannot have the loose paddings. You need your mask to be snug. So a lot of force is introduced that way, crushing the hinge area, and also because the main part of the force, the sum of the force of separating the mask because of paddings, because of your movement, and your movement introduce extra force, extra load. So in this part we have the extra force, and because this part have the force that way, these hinges has to compensate for the force that way, because the overall force is that way. So the loads on the hinges became way larger than they could be in this case, and the mask have a lot of stress in this area. So first, if you have this mask and you want it to be reinforced, what you can do, you can add some metal wire and glue that metal wire with a ultraviolet solidifying glue along this seam at the places where the hinges are. So about 5 centimeters up, 5 centimeters down for the face area, and same for the back side area. So the load that is applied to these hinges would be distributed a bit more evenly throughout the main part of the mask. But actually you can do a way better than this if you move the connection points lower behind the ears, or maybe even to the position around the neck. But before we do this, well, I will show you the typical failure point when you can see the crack here, because this part had a bit too much load, and because this part had too much load, you can, please focus, camera, focus, camera focused. So in this place, you can see this. This part. Well, I do not see look at camera because there is a screen there. So there is a crack, and the crack is because it's the force that was introduced to the seam was greater than the force that actually was separating the mask parts. Because you do not have to just compensate for the force that separates mask part, but also you will have to extra compensate for the force that crushes the hinge down. So this is the next kind of. So here you can see that the position of the hinges is lower, and if you will look here at this position, you will see that the hinges are spread, the top hinge and the clasps are spread relatively evenly throughout the seam. So the distance between these hinges, the hinge and the clasp, and between these clasps is about the same. So about 120 degrees between all them. And from this point of view, it's not 120, it's a bit less, but it's still about 100 degrees between this. So in this case, the loads that separate the front and back mask is distributed more evenly, and the loads at the hinge we have also the separation load, not a crushing load but separation load, and this reduces the amount of load to these hinges as well, because the forces that are applied to the mask, the forces that try to separate the front and back parts of the mask are the same, but we concentrate that forces at different places, and the hinges have no longer need to compensate for that the force that's crushing the main hinge, and we have overall less forces, so it would have less need to, it will be a bit more stable the same material, the same material thickness, the same type of print, but the mask itself would be more stable. And well, in my masks I usually do this. For example, you may see here in this mask, so the hinge, the locking connection. So you can see that the positions of locking connections are almost even. And in this position, this specific position, the main load is distributed through these small locks, and the hinge on top is just in place to make sure that everything clasps together and do not fall off. So, well, it's more for convenience than for keeping both front and back parts together. And this variant is more for the next kind of part. But before this, again, so this is my work. This is the work from Twitter. So you can see there are connections there and two connections near the neck opening, and this you can see two clasps near the neck opening, over to the neck opening behind the ears, and one connection is there as a hinge. And also, if you put your connections closer to the neck, because the neck opening, when you are wearing the mask, the neck opening is one of the most, well, it's usually like the load of open the mask. So when you try to do some stuff and move some stuff, the mask has the initiative to get open, and the lower the hinges are, the more stable it will be, so this connection would stay close. Again, and this is the third variant, when we do not have any meaningful hinge on top of the mask, but we have two hinges, well, about around the same place at the side of the mask. Well, right now in my current mask there is this variant, and those hinges just are placed in a way to distribute the load evenly, so the part of the mask, the back part of the mask, would not push at either at the top or at the bottom. When the load is applied to the mask, the load to open the mask, and these hinges will bear just together just the load of the mask. But also you need to know that basically each single hinge have to be able to keep the whole mask together, because in different circumstances the load may be distributed to one hinge and not to the other. But in this configuration it would be either the all load to one hinge or the load distributed between two hinges. There won't be the situation when one hinge would have to bear the whole load and some extra load because the other hinge is pushed another way. Because in this situation there is no way for this construction to get extra leverage. So basically you see this construction as a leverage. You have, for example, forces to open the mask, then this is the hinge of the lever, and this is the short arm, and this is the long arm, etc. So this is how you should treat your stuff. So you need to place the locking system somewhere around here. There is also inconvenience with placing the locks, the clasps here for the masks with this particular kind of seam, that the face separate and the wick and the head separate. And we shall tell a bit later about this inconvenience. So, well, here you can see this variant, well, in my works. So this is the place of the lock. Well, you know, I use hidden locks usually, so this is its position. And this is how the locks distribute. And about the inconvenience, when you have some hinge here, some regular clasp here, the hair would have the tendency to get in your way, and well, you will have hard time to just keep your hair out of this. So this is about the load distribution. And next, and moving next, we will have the top connection hinge situation, and the points of failure and points of stability to the top connection hinge. Then here I am highlighting one of my masks that are fiber reinforced plastics, and since it's a fiber reinforced plastics, then I can add some extra layers of fiberglass to make this area stronger, and it still is thin, it's still smooth, and I can vary the amount of layers of fiberglass by hand. Basically, some extra layers at this hinge area and less layers further away from it. But when you 3D print this, you will have another situation, and you will have to know how the load and how the stress is propagated through the mask to avoid some concentration, some load concentration, some stress concentration into the mask at the hinge area and other areas as well. So what we have here? This is the popular design. It's published on Thingiverse, and most of Chinese masks have this design of the hinge of the connection between the face part and the back part. And this is my design, and you can see it's not a hinge, but you can imagine a hinge here and it will work completely the same. So what is the differences in these two designs? Well, the first that you will see is that this design is way smoother. And the second, you will see that we have some ribs here, and also we have ribs here. They are not very visible because of how light was worked on Thingiverse, but this part is twice as thick as the regular shell. So what is the difference? Here we have the standard Chinese design, and we see that the mask is thin until we have this hinge area, and at the hinge area, usually at this place the crack is forming whenever the mask is not aligned properly, and whenever the mask gets to move not as designated, but when it's transported usually when it's transported. It's more frequently during transportation than during shipping, during the regular use, but also when you regularly use, you can misalign your parts somehow, or put the mask uncomfortably, and it will crack as well at this point. And here with red you can see the stress distribution propagating throughout this thin part. So here we have a relatively thick part. If it is printed off resin, we have the solid part. If it is FDM printed, we have some air inside. But if you know the structural analysis, the engineering analysis, then you know that what is matter is the top and bottom surfaces, and what is inside is not matter as much as the top and the bottom and the difference between the height difference between two surfaces. Well, basically the railway, the rails and on the railway is the same way. You have a top heavy, a bottom heavy, and a thin membrane between them, and they work perfectly. And these kinds of beams also work perfectly. So we have this height separation. And in this area, the stresses that are introduced to the mask are relatively small, because the forces that can be introduced to the hinge and that are introduced to the hinge dissipate through this relatively large amount of material. But we have a sharp corner here, and as we get to that sharp corner, we have a spike in the stress throughout the material, and this spike can be pretty large. Firstly, because the material is not rock solid, it's a bit flexible, and this part flexes way more than this part. This part basically felt as a rock solid, when this part is pretty flexible and it tried to flex, and since it cannot flex much through this material, it has to bend at this point, and also at this point there is the maximum stress. So it has a spike, and then it dissipates throughout the material. So when we have this spike of the force, the spike of the stress inside the material, we have a potential crack, and we have those cracks. When in my design with more smoother, and in the clever design, first of all we have it smoothly to thin smoother, so there would be no place for that spike to form. It is basically dissipated through a larger area. So well, this and this, the area under this curve are the same, but this we have a lot higher spike, a lot of higher force, because this part is lower, and here we have almost uniformly distributed load, and also the ability of the material to flex gradually reduces from the main mask to the hinge area. And we do not need to make this thick all the way to this, all the way through all the material. We can just make a beam here, extra rib here with this profile, a rib here, and a rib here, and all this, because the top of the mask works basically like a cage with some membranes that are stretched from one rib of the cage to another rib of the cage. So again, taking Alice here, you see that there is a lot of holes in it. So it's basically a cage. We have a large rib here, a rib here, here, and here. And between those ribs, we have these areas with some membrane-like areas with that are basically a mesh that do not need to be thick, because those parts are here to support something, but they do not need to be very durable. That I just support the hair, but also you can see that there are some slits here. Well, 1, 2, and 3 slits, and these slits are for placing some extra parts, for cat ears in particular, and those slits are more connected to the ribs, and actually inside of this is some extra reinforcement with fiberglass to make these specific areas a part of the rib cage, but not a part of the membrane. Well, So here we can see this standard for Chinese masks printed hinge and the standard for Chinese masks point of failure. Well, camera focus. Standard point of failure. Some cracks at this position. Well, also speaking about ribs, so this is the screenshots of my mask design. I introduced to Thingiverse. Just find the meet Kigurumi mask and you will see this design, the face part of the mask. So you can see there are a lot of ribs coming from different parts. It's also reinforced along the edge, reinforced along this edge as well. It's not seen on the screenshot, but trust me, it is there. I did it. And some ribs here, some net of the ribs, and there is relatively thin areas between these ribs because the main load that mask can have is distributed through those ribs, and the rest of the mask would just redistribute because we have relatively small areas of these thin membranes between the ribs. And this is the back part, and you can see these red lines. These red lines are where we're supposed to extra reinforce the back part with a metal wire, because at these parts we have some slits. At these parts where we are going, we need to put some wires or some threads to secure the wig on top of the mask. So there would be some extra forces to rip that wig off the mask, well, because, well, it's a separate part, so we need to, and it's a flexible part, so it won't be crushing down the mask, but it may want to get ripped off during a windy weather or during a convention or during some harsh interaction, whatever you are going to use this mask. So we need to reinforce these elements, some extra reinforcement to dissipate the forces throughout the other mask, parts of the mask, throughout those ribs. Furthermore, from the points of connection, that the larger area you dissipate the force, the smaller the force itself is into this position. And also, you can see we have some extra points. These extra points there are supposed to be some holes in these positions. You do not see it, but on the model there are holes. Well, at these points we have some mounting posts for some extra, like cat ears, maybe some headdress, maybe some ponytail, etc. And to be able to install that and to let them rest there securely, we also connect the ribs to these specific positions. Well, and now the design that is to the comparison, the regular design of, well, the regular design from Thingiverse. There is some copyright of the maker here, but if you would search the Kigurumi mask on Thingiverse, then you will find this model, the characteristical triangular holes that are, well, that are believed to be for the ventilation, but actually these holes are for reducing the weight of the mask. Well, believe me, because I was the one who introduced a lot of holes in the backside of the mask more than 1.5 decades ago. So, well, I know what I'm talking about and why I introduced those holes and why those holes became the situation and what people were thinking about this. Well, I remember all the conversations. So basically, there is nothing wrong with these holes at all, because it's a great point of connection of some external elements it's a great to attach, to secure the wig on top of the mask. It's a great thing to add some horns, some cat ears, dog ears, etc., some ponytails, all this stuff. They will help you a lot to put this on the mask and attach it to the mask, and also you can fit some breathing tubes through these holes as well. So there is nothing wrong with these holes, but just bear in mind that are not for ventilation, actually. And you can see that there is no smoothing between the hinge and the mask, no smoothing between the hinge and the rest of the mask. There is also some extra points of connection here. And when this mask would have some extra load from the usage, we will see these pictures. We can see this part to crack off just on this part, or there can be a crack just on the tip of this thing. We can see the crack here because there is nothing to reinforce this edge. We also will have cracks here, something like that, and that crack will go through the holes because it is less amount of resistance for the crack. You can get here, but it's easy to go from hole to hole to hole to hole to hole. And also you will have cracks here for the same reason, because here are the points to connect the clasps, and in this design the clasps are again too high. So when the mask will be put on and the laws that try mask to separate would be introduced to the mask, then this area would be crushed and this area would be stretched out. So here we will have also some cracks, and also this edge is not reinforced at all. So when you would hit your head a bit too hard against the wall, you may get some cracks forming from this edge up to the mask, simply because this edge is not reinforced. You do not need to reinforce the whole of the mask. You need to reinforce the edges, and you need to add some ribs along these places to make it more stable. And this is the examples of the cracks, simply because we didn't have the reinforcement along this part. Well, and here we also have some cracks, as I remember. Yes, this part cracked off and then glued back. And simply it is because we do not have the extra reinforcements propagating from this part to the main mask, and we do not have that smoothed out ribs and smoothed out thickness. So the thing I want to, this is the thing I want to focus, is that you do not, there is almost no critique on the design of the exterior, because it is what we are allowing our masks for, the exterior, how they built, but the inside of the mask must be built not within the aesthetics, but with the engineering in mind. Well, the reason the masks are made this way is because people who 3D model those masks are usually artists, but not engineers. So, and when you 3D model a Kigurumi mask, you make the outer surface, you make the face, you make it smooth, you make it nice, and then you just extrude it inside, about 5, maybe 3 millimeters inside, and call it a day. But actually, the 3D printing process, when you 3D print a shell, a large thin shell, you have a lot of stresses inside the material as well, because the nature of the 3D printing, especially resin 3D printing, but also it is also true for HIPs or ABS plastics, that the material tend to shrink during the process, and the layer that already solidified or cooled down try to shrink when the layer on top of it, that is for the FDM, is on top, for the SLI it's on the bottom. The new layer is not solidified yet, it's in its liquid state or viscous state, and it gets on top and then try to shrink. Then we have some warping action. Well, basically, in bad case scenarios, at the first 3D printed Kigurumi mask, you may heard that the mask made by Raigeki, when he was shifting towards 3D printing, once explode on his head. Well, not exploded, just cracked during the festival because of temperature differences outside and inside. Because at that time there was no special techniques to treat these heat problems, and also and also there was another story with the resin 3D printed masks, and well, it's not a story, it's basically a trend that the masks get shipped to. When the masks get shipped to our country, they may be handled poorly and may be squished and tossed around, and because there are some internal stresses in the material already, we can get the cracks of the masks, and masks can be repairable or can be not repairable. I also have this story as well, and it is a story for another lecture, but the baseline for my talk here is that you need to design the mask interior keeping in mind all the forces that may get to your mask, because when you do the resin casting, or when you cast it out of polyurethane in a silicone form or something like that, you do not need to be bothered about the stresses introduced by the fabrication process, because all the molecular chains are almost random, and when you have a fiber reinforced plastic, you have extra fibers to keep everything in place. But in 3D printing there is no luxury like that, and you either have a more durable materials like nylon that is hard to paint, or you will have to stick with the materials that are a bit brittle. So you need to design the ribs inside the masks accordingly. And so this is what I want to talk to you about, and thank you for watching. And I hope that if you would make a Kigurumi mask, you will keep all that in mind, and your mask will be stable, durable, and will last for decades or maybe even centuries. Thank you.